Welcome to section 2.3 part 2. Apparently I talked too long and my recording program cut me off after 15 minutes, so I'm going to talk faster now. So we were on this limit law that looked at the limit of the identity function, and this tells us that the limit as x approaches a of x is just that value a that x is approaching. And that kind of makes sense because if we look at the graph, y equals x always. So if x is approaching any number a and y equals x, then y is approaching that number as well. So this law helps us answer that second part of our problem from before. The limit as x approaches 2 of x. Well, that's going to tell us that that limit should be 2. So let's go back to that. Now we can finish that example. So we'd gotten to this point. The limit as x approaches 2 of x plus 1 to the fourth. So applying that constant function law tells us this limit's going to be 2. And applying the identity function law tells us this limit's going to be 2. And applying the constant function law tells us this limit's going to be 1. So we're going to end up with 2 plus 1 in those brackets raised to the fourth power, or 3 to the fourth, which is 81. So the next law tells us that the limit as x approaches a of x to the n is just a to the n. And that we can derive by using that power limit law that we saw in law 6, I believe it was, with the identity function f of x equals x. So in other words, I can bring the limit of x inside the brackets and raise that to the nth power. So looking at examples always a little bit better. So the limit as x approaches 2 of x cubed, this is just telling me that I can take the limit as x approaches 2 of x, which we saw by the identity function law is just 2, and then raise that to the third power. So my answer is going to be 8. And then finally, the last two laws are limits of nth roots. So we have the limit as x approaches a of the nth root of x is equal to the nth root of a. And the limit as x approaches a of the nth root of f of x is just the nth root of the limit as x approaches a of f of x. So again, we are pulling those limits inside the radical and evaluating those limits inside the radical and then taking the radical. So let's put some of these things together. Let's evaluate this limit, x to the fourth plus 3x minus 5 as x approaches 1. If you're asked to evaluate a limit and to justify each step, this is what you would do. You'd say, well, I'm going to first apply the sum and difference law and break it up into the limit of the sums or differences. Then I'm going to look at each limit, and this first limit, I can apply that power law that said I can just replace x with 1. So 1 to the fourth power is just 1. For this second one, I'm going to apply the constant multiple law, so I can pull out that 3. And then I'm going to apply the identity function law and say that this inside limit's just 1. And then for this last term, this is a constant function, and the limit is just that constant. So putting it all together, I'm going to add 1 plus 3 minus 5 to get minus 1. And we can verify that graphically. Here's another example. Now it's a rational function. So since my limit is x approaching minus 3, and minus 3 is a 0 of this denominator, we can't use the quotient law yet. because we can't find the limit as x approaches minus 3 of that denominator. It's 0. So first we have to do some algebra, and that is a big part of these limit problems. You're going to have to do a lot of preliminary algebra a lot of times to get to the limit. So we factor the numerator and denominator, and notice we have a common factor of x plus 3. So that means that x equals minus 3 is a whole. So we can cancel those and we get this simplified function. So the values of this function all around x equals minus 3 are the same as the values of this function around x minus 3, right? X minus 3 is a whole here, but all the other function values are the same between these two. So that means I can find the limit of this simplified function, and it's going to equal the limit of this original rational function. So let's look at that limit. Now I can use the quotient rule, the quotient limit law. So I can take the limit of the numerator and the limit of the denominator on that simplified function. And again, using the identity function law in the numerator and the sum or difference law in the denominator, and then again the identity function law and the constant function law, and I get 3/7. So you can verify this graphically as well. So looking back at these examples, there's one thing that I'm sure you've noticed, that a lot of times you can just plug in the value that x is approaching into the function, and that's your limit. And that's because these functions that works for the most part, have been polynomials or rationals. And they're continuous there. We're going to talk about continuity in the next section. But they have no breaks in their graph. And you would have seen that concept before in pre-calculus. So if you have a polynomial function, you can just simply use direct substitution to find the limit. You don't have to justify every single step by using the sum and difference and constant multiple rules. And the same for rational functions if a is in the domain of the rational function. So in other words, if it's not a 0 of the rational function, I can just plug in, or excuse me, the denominator of the rational function, I can just plug the value of a into the rational function. However, if x equals a is a 0, and there's a hole at x equals a, I can just substitute a into that simplified function after I cancel that common factor. We saw that in the previous example. So another tactic we use, if we have more exotic functions, if we don't have just a polynomial or a rational function, you also want to look at one-sided limits. So an example might be this function. So if we find the limit as x approaches 0 of the absolute value of x over x. That's not a polynomial, it's not rational. I don't have any limit laws about absolute values or anything. So we need to define this as a piecewise function. So the absolute value of x over x equals +1 when x is greater than 0, and it's -1 when x is less than 0, and it's not defined at x equals 0. So when we look at the limit as x approaches 0 from the right, that would be 1, yet the limit as it approaches 0 from the left would be -1. So this limit does not exist. So this is just kind of summarizing the various techniques we've had for finding limits. The easy case is when it's a polynomial or a rational function and x equals a is in the domain. A couple more tools that we talk about in this section. Since limits are really just talking about the y values of functions on a graph, this rule is telling you that if one function if all the y values of one function are less than all the y values of another function for some interval on the x-axis, then the limit of, in this case, g of x would be less than the limit of f of x. It just makes sense. So for example, when x equals 3, the limit as x approaches 3 of g of x is going to be less than the limit as x approaches 3 of f of x, because all the y values of f are greater than all the y values of g around x equals 3. However, if you look at x equals 1, that's not the case. On one side, g of x is greater than f of x, and on the other side, f of x is greater than g of x. So if you were going to look at that limit, you'd need to look at the one-sided limits. And that leads to a big deal theorem called the squeeze theorem. And that basically tells you if all the y values of a function, in this case g of x, are between the y values of two other functions, so in this case f of x, all the y values are greater than g's, and h of x, all the y values are less than g's. But if f and h both have a same limit as x approaches some value, then g must have that same limit. So looking at this example, g falls between f and h for all values. So the limit as x approaches pi of f and h is 0. Therefore, the limit as x approaches pi of g is also 0. That's called the squeeze theorem. G is squeezed between f and h. So here are some additional examples that show how you need to use preliminary algebra. So remember, given this problem, you can't just use the quotient law because the denominator has a limit of 0. But if you expand that numerator, you'll see that those 16s cancel and that you can cancel a common factor of h from the numerator and denominator. So then the denominator is no longer 0, and you can just evaluate that by direct substitution. Here's another example where you need to multiply the numerator and denominator by a conjugate. So what that does is introduces more terms into the denominator so that the denominator is not necessarily 0. So notice in this case, as x approaches 9, I can't just take the limit of that denominator. I can't use the quotient law because the limit of that denominator is 0. But if I multiply the numerator and denominator by the conjugate of the numerator, then notice what happens is I get a common factor that cancels, and now this denominator does not have a limit of 0. So take a look at that a little bit more closely. So summarizing, we have a bunch of tools that we've looked at. We have those laws. We've determined that we can use direct substitution for polynomials and rational functions, which is very handy. We need to perform preliminary algebra a lot of the time so we can cancel factors in the numerator and denominator before we can apply that quotient rule. We saw these laws for actually helping us determine limits without having to resort to a graph. Finding one-sided limits, usually that's handy for functions that involve absolute value or piecewise functions, and then the squeeze theorem. So that is it, and I'm also running on 15 minutes, and I will see you in section 2.5.